Okay, so I'll give you all a second to write that down. The first thing you're going to have to do is take those words and write a balanced chemical equation with that problem. Okay, so everybody's got the problem written down. I can switch slides here. The first thing I told you you needed to do was to write the balanced equation. So, y'all probably came up with nitrogen plus hydrogen makes ammonia, NH3. And then to balance that, it's simply a 3 here and a 2 here. Okay, so everybody should have gotten to that point. Now, I'm going to go back. I'm told that hydrogen's rate is 0.082 meters per second. Okay, so I'm going to go over here and put underneath my hydrogen that I know that is, I'm sorry, not meters, molarity, 0.082 molarity per second. That's what I know about hydrogen. The question asks for both the ammonia, its rate of formation, and nitrogen at what rate it's being used up. So the first question asks about ammonia, right? Do you see that using my coefficients, I know 1/3 the rate of hydrogen is equal to 1/2 the rate of ammonia? Isn't it? It's 1 over the coefficient for whatever I've got for the components, right? Now, setting it up like this, 1/3 of H2 is equal to 1/2 of the NH3. Y'all, what of this statement do I know? The H2 I know. The problem told me that H2 is 0.082. So I'm going to plug in that 0.082 for my H2. 1/3 of 0.082 molarity per second is equal to 1/2, and I'm going to write X, because I now know that X is my ammonia rate. Mathematically, what do I punch in my calculator? I say 0.082 divided by 3 times 2. That's mathematically what I punch in, 0.082 divided by 3 times 2, and what do you get for X?
0.0547.
Yes, 0.0547 molarity per second. How many of y'all got that one right on your own? Awesome. Well, awesome that y'all got it right, but not so good that only 3 or 4 people just raised their hand.
So you get that by timing 0.082 times 3?
No, 0.082 divided by 3,
Divided.
and then times 2. I mean, just look at it out algebra, right? You just have to solve for X. You good? Okay, now that you know that, huh? Yes, yes. If you didn't have B before, let me pause a second and let y'all try to get B on your own. Because after I've shown you A, now your memory is back up to speed and you can do B. Okay, guys, the next part, B. B asks me at what rate is nitrogen reacting. So for B, I've got to figure out nitrogen. Well, again, using my stoichiometry, can't I see that 1/3 of the hydrogen is equal to nitrogen? Can you see that? 1/3 of whatever hydrogen is going to be equal to nitrogen. Since nitrogen's coefficient is 1, I'm not going to put 1 over 1. Right? I'm just going to leave it like this. So 1/3 of 0.082 is what nitrogen's rate is. What did you get for the rate for nitrogen? 0.0273. I've walked away from my calculator. Is that right?
Yes.
0.0273 molarity per second. That's it.
I use the ammonia
Okay.
instead.
Okay, then if you can actually use this number. Hang on, I'm going to change colors.
Came out the same answer.
It will. It will. You can go from here, which is the ammonia, to nitrogen. 1/2 of this number is going to get you there. So it's because you're always dealing with the coefficients, it doesn't matter really which one you start with, but as Peyton said just a second ago, I like to go back to my original problem, the .082, because what if I got A wrong? Then I'm going to use the wrong number for B. So I like to go back with where I started to calculate the other numbers, okay? You're going to encounter some problems in your book, y'all, when you're working those practice problems dealing with this. You can use the rates to figure out the reaction stoichiometry. If you know that nitrogen is .0273 and ammonia is .0547, if you divide those numbers out, you'll see that it takes 2 nitrogens to get you here, and so that you know the coefficient of this would be 2. Do you see how the rates follow right along with the stoichiometry? So therefore, you can use rates of reactions to figure out stoichiometry. Do y'all see that?
Yes.
Okay. I think you're just being nice by saying yes, but okay. That's comparing rates of reactions. Now we're going to talk about something called a rate law. And if you'll remember last time, I wrote this little generic equation on the board. I said A moles of A plus B moles of B makes C moles of C and D moles of D. Remember that from last time? And that's what we just finished practicing, is using the coefficients to figure out rate. And y'all will recall that the lowercase letters are the coefficients and the uppercase are the components of the reaction. Well, this is how that's going to break down to what's called a rate law. A rate law looks like this. The rate is equal to some constant, K, times the concentration of A raised to the X power times the concentration of B raised to the Y power. So notice, when we are coming up with a rate law, the only stuff that shows up in the rate law is the reactants. We don't put products in a rate law at all. It's just the reactants that show up in the rate law. And you'll remember, you see here, I've got square brackets around A and square brackets around B. What do the square brackets around something mean? They mean concentration. Concentration, what kind of units are we using for concentration in these problems? We've been using it, and it's molarity. Okay, we'll be using molarity for concentration. K is a rate constant, and I'll show you more about that in its units in a minute. The rate, well, that's the same kind of rates we've been using, right? It's some kind of change in concentration over time. So the units of rate are like molarity per second, or molarity per minute, or molarity per hour. It just depends on what kind of reaction you're looking at. X and Y are obviously exponents, but y'all, do you see that in a rate law, the little a and the little b, they're not showing up anywhere in the rate law, are they? So the point I'm trying to make by pointing that out to y'all is that the coefficients do not matter for the rate law. Got it? Coefficients do not matter. So where do you get X and Y? X and Y have to be determined experimentally. And I'm going to show you how to do that in a second. So I'm going to use an example out of the book to explain to y'all how you come up with a rate law. And the table I'm going to copy on the PowerPoint, or whatever you want to call this, is on page 587. So the bottom of page 587 in your book is the table I'm going to copy here for us to look at. Okay, we're going to use this chart to come up with a rate law. And let me give you a real simple example of how we go about doing this. Okay? Guys, let's say that our favorite cookies are oatmeal cookies. This is a good example, yes? Okay, and so I always make really good oatmeal cookies. True story. But last week, instead of buying the Quaker brand, I bought the Kroger brand. And I used a different kind of butter than I normally use, and I even used a different pan. I used one of those stone pans. And so the cookies came out flat. Now, why did the cookies come out flat? Well, that's what I'm thinking. I'm thinking it was that Kroger brand of oatmeal that I bought. But could it not be that stone pan? Because I changed 3 things. I changed the butter, I changed the brand of oats that I used, and I changed the type of pan that I used to bake the cookies. So can I for certain say those cookies were flat because of the Kroger brand?
No.
I can't say that for certain because I changed 3 things with the way I make oatmeal cookies. Okay? What does that have to do with what we're doing? We're going to look at this data. Do y'all see that what I have on each line is 3 different experiments? Okay? So this first experiment, I took these 0.1 and 0.01 concentrations of my reactants. They were allowed to react, and I got this rate. The second experiment, I changed the concentrations to what I see here, and I got a new rate. I got a different rate for each experiment. If I wanted to look at, say, how come experiment 1 and 2 are different rates? Look at experiment 1 and 2. What changed about experiment 1 and 2? The only thing that changed for these experiments is the concentration of the ClO2, right? So therefore, I know that this change in rate is due to the difference in the ClO2 concentration. Okay? Could I compare experiments 2 and 3? Look at experiment 2 and 3. What changes? The fluorine changes, right? The ClO2 changes. So why did this change? Well, you don't know because you changed 2 variables. So you can't attribute the rate change to either one because you don't know which one caused it to be different. Does that make sense? You can only vary one thing, one reactant at a time. Okay, let's see how we're going to use this. If I give you the balanced equation, you have that up there. Do you guys see that the rate law is going to look something like this? The rate...
A coincidence that the rate of number 2 and 3, well, 2 is double 3, and then in the F2, the number
that 1 and 3 are doubled? It's not a coincidence. No. I'm going to, when we're all done with this, with me explaining this, you'll see that. You'll see why it is. Do you guys see that the rate law is going to look like rate is equal to K times the concentration of F2 raised to the X power times the concentration of ClO2 raised to the Y power. It has to look like that because that's what we just said on the previous slide that a rate law would look like. I'm going to use the data in this table to figure out what X and Y are. So how am I going to determine what X is? Well, according to what I've written here for my rate law, X tells me what changing the fluorine concentration does to the rate, doesn't it? Because X goes along with F2. Now, look up there at the table. In what 2 experiments do I change the fluorine but leave the ClO2 alone? Between 1 and 3, the fluorine concentration changes, but nothing happens to the ClO2. Agreed? So I know that whatever that change is, that is the reason that this rate changes. It's solely due to the fact that I changed the fluorine concentration. How did I change the fluorine concentration? What did I do to it? I doubled it, and I can see that. I know y'all see that 0.1 to 0.2 is double, but look, 0.2 divided by 0.1 is 2.
Why did you put 3 on top?
I want the bigger one on top so that I can get a whole number right here. Okay, so 0.2 divided by 0.1 is 2. Do y'all see where I'm writing in the bottom left corner? What did that do to the rate? It doubled it as well, didn't it? Because if I put experiment 3 on top here and divided it by experiment 1, then when I go over here to my rate, I've got to put experiment 3, 2.4 times 10 to the minus 3, divided by experiment 1, which is 1.2 times 10 to the minus 3. Oops. And of course, this is adding a lot of writing out what y'all can see, because y'all know that 2.4 times 10 to the minus 3 divided by 1.2 times 10 to the minus 3, y'all know that is 2. What does that tell me? 2 raised to what power gives me 2? Now that's how I know x is 1. 2 raised to what power gives me 2? X is equal to 1.
So you always put the bigger number on top?
Always put the bigger number on top so that when you divide them out, you will have whole numbers when you get down to this point. 2 raised to what power gives me 2? Another way it can work out, sometimes it'll say 2 raised to what power gives me 4? And then what would the answer be? 2. So x would have been 2 if that's how it worked out. Okay? So now in doing that, we know that x is equal to 1. And I've tried to color that in really big. X is equal to 1. Y'all, what 2 experiments am I going to compare to figure out what y is? Does everybody agree? Yes. That I have to compare experiments 1 and 2. Because right here, fluorine stays the same.
How come we, like, where does the K come in?
Huh? I'm going to show you that. We're not there yet to K. Are you okay on how to pick the experiments? For why I've got to look at 1 and 2.
And that's because there's the only thing that's changed?
Because
Is
ClO2
ClO2?
changes. Yes, ClO2 changes, fluorine does not.
Okay.
With me? Now, y'all can look at those numbers. What has happened to ClO2?
It's been changed from...
It's been changed by a factor of 4, hasn't it? Do you see that? And how could you write that out like I've done it over here? Wouldn't you say 0.04 divided by 0.01 is 4? Okay. I'm getting down into my little logo there. It's hard to see. What happened to the rate? 4.8 times 10 to the minus 3 divided by 1.2 times 10 to the minus 3. What's that a factor of? 4. Four raised to what power gives you 4? 1. So now I know that y is also 1. Look at the coefficients in the equation. X and y had nothing to do with coefficients. If they did, then the exponent on ClO2 would have been 2. Do not use your coefficients for your rate law. So how do we calculate K? Well, guys, now that I know the rate law, its rate is equal to K times fluorine raised to the first power times the ClO2 raised to the first power. I can calculate K because in that table up there, I have a rate for each experiment and I have a concentration for each experiment. So don't I have a number to plug in for the rate, a concentration to plug in for the fluorine, and a concentration to plug in for the ClO2? I can plug the numbers in from the table and solve for K. Now, which experiment do I use? If you have figured out the rate law correctly, it should not matter. And so to prove that to you, the first table up here, you 4, are going to calculate K based on experiment 1. Table 2, y'all use experiment 2, and the back table, y'all use experiment 3 numbers. If we have done the rate law correctly, then every one of us should get the same value of K. Okay, I used experiment 1 data to plug into the rate law that we just figured out. Table 2, y'all used experiment 2 data. Do y'all see that? Table 3, everybody sees you might have had different numbers from what I have on the board, but every one of us should have got that K is equal to 1.2. Guys, this is a way to check yourself. Because if you come up with a rate law, maybe you came up that fluorine has an exponent of 2. If you'll check it and calculate K for 2 different experiments, if that K doesn't match for 2 experiments, then that means, whoa, I got the rate law wrong. Okay, so do you see that that's a way to check your answer? Because you're going to have a problem like this on the test, I promise. Now, Kelsey asked, what are the units? Look at what the units are. I took a rate in terms of molarity per second, didn't I? And I divided it by a molarity times a molarity. So didn't I divide it by a molarity squared? Okay? So one of these m's cancels with one of these m's. So my units are m minus 1, s minus 1. What does that little minus 1 on the m mean? It means that it's on the bottom, that it's in the denominator. Look at what I have here. The m I have left, isn't that the m in the denominator? This s, isn't it in the denominator as well? So the units here are m minus 1, s minus 1. Are the units for the rate constant always m minus 1, s minus 1? Unfortunately, no. There is something called an overall reaction order. An overall reaction order, y'all, that is the same thing as saying, the sum of the individual orders. Like that helps. What is that saying?
So when it says m minus 1, m minus 1 half of s minus 1, that's not like a fraction line, is it?
No, I left a blank there. That blank is a blank. Overall reaction order is the sum of the individual orders. Y'all, for this one that we just did, the overall order is 2. Do you know where I got that from? Because the exponent on fluorine, the x is 1. And the exponent on ClO2 is 1. And what is 1 plus 1? 2. That is what overall reaction order is. It's just the sum of the individual orders or the sum of the exponents.
So pretty much overall reaction is just x plus y.
Exactly. There you go. X plus y.
Will we ever get like negative?
No. You can have 0 though.
Okay.
Okay? For what we're doing in here, good question. Your reaction orders will always be 0 or a whole number. 1, 2, 3. You will not have fractions in terms of x and y in this class. They can be, okay, but we're just not going to do those. So let me just give you a breakdown of what that means for units. If the overall order is 1, then the units for the rate constant K are going to be time to the negative 1. And I'm putting time. Why didn't I just write a time? Exactly, because it can be seconds or minutes or hours. So if the overall order is 1, it's just whatever unit of time was used for that experiment to the negative 1. If the overall order is 2, the units will always be m minus 1, time minus 1. That's what we just saw. If the overall order is 3, the units will be m minus 2, time minus 1. No. I will not give you this table for the test. If the overall order is 4, the units will be m minus 3 time minus 1. Do you see the pattern now?
Yeah.
Okay, so if the overall order is 5, what would the units of the rate constant be? M minus 4 time minus 1. So the time, y'all, is always going to be to the negative 1, but the m, it depends on, did you cube the molarity or raise it to the 4th power or square it or whatever. So the m is all that's changing.
So, was that actually our final answer?
Huh? For the previous one? M minus 1, S minus 1.